The morning of June 15, 1944, the air over the western beaches of Saipan was thick with the smell of high explosive and pulverized coral. It was not the crisp, cool scent of European battlefields, it was a humid, heavy heat that choked the lungs. The 2nd and 4th Marine Divisions were ashore, holding a narrow, blood-soaked beachhead, and every man knew the counterattack was coming. But they had confidence, not just in their discipline, but in their machines. In the dunes, their M4 Sherman tanks, hulking beasts weighing nearly 32 tons, moved into position. They mounted 75mm guns and possessed frontal armor up to 2 inches thick, angled effectively. These were war machines built to absorb punishment. They represented the industrial might that had been promised to every American fighting man. First CTA, if you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Just before dawn on June 17, the jungle darkness was suddenly violated by a sound the Marines had dreaded since Guadalcanal, the clanking, grinding roar of enemy armor. Lieutenant Colonel William L. Jones, commanding a battalion of the 6th Marine Regiment, could hear the enemy's entire mechanized force bearing down on his perimeter. It was the Japanese 9th Tank Regiment, a formation composed of about 44 tanks, mostly the ubiquitous Type 95 Hago light tanks. These were the tanks that had spearheaded the sweeping, triumphant advances across Malaya and the Philippines 3 years earlier, navigating terrain Western engineers had dismissed as impassable for armor. Japanese commanders believed in these machines. They believed in the tactical doctrines that favored speed, mobility, and the element of surprise over brute protection. This was to be the largest, most determined armored charge Japan ever committed in the Pacific. Inside the Marine lines, however, were not just Shermans, but the most common, most prosaic heavy weapon in the American arsenal, the Browning M2 heavy machine gun. This weapon fired a half-inch caliber round, a .50 caliber bullet. Its primary battlefield roles were supposed to be anti-aircraft defense and long-range suppression of infantry. It was a machine gun, an infantry support weapon, not an anti-tank cannon. Its presence was taken for granted. It was simply part of the massive logistical tapestry woven by American production. The official doctrine for dealing with enemy tanks required bazookas, sticky bombs, or the specialized 37mm anti-tank guns. Yet, when the 44 Japanese tanks charged out of the darkness, something happened that defied doctrine and shook the psychological foundation of armored warfare in the Pacific. The Marine gunners, firing their heavy machine guns at the advancing Hagos, began to see clean, decisive penetration. The bullets did not ricochet, they did not dent. They punched right through the Japanese armor. The sound wasn't the expected clang of steel against steel, it was the sickening, high-pitched thwack of penetration. The crews inside the cramped, 9-ton Japanese tanks suddenly experienced a phenomenon they had been trained to believe was impossible: death delivered by a standard infantry machine gun. This battle was about to reveal a fatal, critical flaw in the entire Japanese armored doctrine. The question was not how the Marines stopped the attack, but why a machine gun could stop a tank designed for modern warfare. To understand the profound shock of Saipan, one must first grasp the foundation of belief upon which the Japanese Hago tank was built. Its design was not an accident, it was a deliberate choice rooted in the specific military and logistical challenges faced by the Imperial Japanese Army in the 1930s. When the Type 95 light tank was conceived in 1933, the primary theaters of operation were Manchuria and China. The expected enemy forces possessed negligible armor and limited anti-tank capability. The priority was not protection against high-velocity armor-piercing rounds, but speed, mobility, and reliability in harsh, underdeveloped terrains. The Japanese engineering principle was one of optimized, minimalist design. A tank that was fast, light, and could be mass-produced within the constraints of Japan's nascent heavy industry was deemed superior to a heavy, slow tank. The resulting Hago weighed a mere 7.4 tons and was powered by a reliable Mitsubishi air-cooled diesel engine, prized for its reduced fire risk and availability of fuel in remote areas. Its armor was thin by necessity, just 12 mm at its maximum on the turret and frontal hull, tapering to 6 mm on the deck and floor. Japanese designers calculated this thickness was more than sufficient to resist standard rifle and machine gun fire at combat ranges. Their early combat experience in China starting in 1937 only reinforced this belief. The tanks proved devastatingly effective, allowing commanders to assume that their emphasis on spirit and tactics could overcome any theoretical material deficiency. The armor worked against the enemies they expected to fight, fostering a dangerous, deeply entrenched psychological narrative. The Hago was invincible in its intended environment. This foundational belief was momentarily challenged at Kochan Gol in 1939 when Japanese forces clashed with the Soviet Union. Facing Soviet BT series tanks, armed with 45mm guns and thicker armor, the Hagos suffered significant losses. The lessons of material inadequacy were clear on the battlefield. However, Japanese military leadership, fixated on doctrinal improvements and the continuation of the war in China, failed to initiate a fundamental, fleet-wide redesign of its armored forces. They preferred to rationalize the losses as a tactical failure in the face of overwhelming artillery, rather than an obsolete design flaw. The belief persisted: the tank's thin armor was a necessary trade-off for its crucial mobility. Furthermore, they did not anticipate the sheer scale and quality of weaponry the Americans would deploy as standard equipment. The American war machine, largely unseen before 1941, operated on a completely different scale of material abundance and engineering doctrine. The coming confrontation on Saipan would not just be a clash of armies, but a violent collision between Japan's doctrine of minimalist optimization and America's doctrine of industrial overkill. The instrument that shattered the Japanese belief system was not the M4 Sherman, nor the bazooka, but the ubiquitous Browning M2 heavy machine gun. Its role in the Saipan counterattack revealed the astonishing material and psychological gap between the two warring powers. The M2 was designed by John Moses Browning during the First World War and was perfected over the following 2 decades. It fired the .50 caliber cartridge, a massive round by infantry standards. The bullet itself was a half-inch wide, and when fired, it achieved a muzzle velocity exceeding 2,900 feet per second. But the key detail, the one that the Japanese engineers had failed to account for, was the American use of the armor-piercing (AP) variant of this ammunition. The .50 caliber AP round was specifically engineered to defeat lightly protected targets like aircraft or unarmored transport trucks. It featured a hardened steel core jacketed in copper. American ordnance testing had verified that this standard AP round was capable of penetrating up to 23 mm of face-hardened steel armor plate at a range of 200 yards. The physical reality was unforgiving. The maximum armor on the Japanese Type 95 Hago was 12 mm. Simple arithmetic dictates that the American machine gun round possessed nearly twice the penetrating power necessary to defeat the tank's thickest point. This reality was utterly foreign to the Japanese tankers. Their training and experience had conditioned them to view small arms fire as merely a nuisance, something that created loud impacts on the hull exterior but posed no threat to the crew. Their only defense against small arms was the psychological comfort of their 12mm plates. On the night of June 17, this psychological shield became useless. Marine machine gunners, positioned in foxholes and behind low earthworks, targeted the advancing Hagos at point-blank range, often less than 150 yards. The effect was immediate and devastating. The half-inch rounds ripped through the thin armor, entering one side of the tank and often exiting the other. Inside the cramped Hago hull, the penetrations were cataclysmic. A round that defeated the armor transformed into a lethal piece of shrapnel, ricocheting through the crew compartment, striking the engine, detonating ammunition, or hitting the commander or driver. The Japanese tankers who survived later expressed genuine shock and disbelief to American interrogators, many believing the Marines possessed a new, secret anti-tank weapon. They simply could not reconcile the idea that an infantry support machine gun, a weapon they saw mounted casually on jeeps and half-tracks, could defeat their primary battle tank. This encounter on the beaches of Saipan marked a brutal, material awakening for the Imperial Japanese Army, a realization that the speed and spirit doctrine was obsolete against the sheer industrial density of American firepower. The Japanese 9th Tank Regiment that charged the Marine lines on Saipan was, by Pacific standards, a formidable mechanized force. It was commanded by Colonel Takashi Goto, an officer whose training and professional life had been entirely defined by the doctrine of maneuver and surprise perfected in Manchuria. His regiment comprised mostly the Hago light tanks, but also included some of the heavier, yet still thinly armored, Type 97 Chiha medium tanks. The Chiha mounted a more potent 57mm gun, but shared the same core vulnerability. Its thickest frontal armor was only 25mm, less than an inch, and its side armor was comparable to the Hago's 12mm. The crews of the 9th were not green conscripts, many were veterans of the battles in China, where their tanks had been instruments of terror and decisive victory against poorly equipped forces. They were psychologically attuned to winning through speed and audacity. The specific lie, or rather the fatal self-deception, they carried into that night was about material parity. Japanese propaganda and internal military briefings consistently emphasized that Japan's technological advancements, coupled with the superior fighting spirit, seishin, of the imperial soldier, were sufficient to overcome the sheer volume of American production. This was a narrative necessary for survival, given the overwhelming industrial disparity. Consider the sheer scale. During the years 1941 to 1945, Japan produced only approximately 2,500 tanks of all types. In contrast, during the same period, the United States produced over 50,000 Sherman tanks alone, alongside thousands of other armored and support vehicles. This gulf in production meant that every single piece of Japanese equipment, including the Type 95 tank, had to be conserved, maintained, and repeatedly utilized far beyond its design obsolescence. The American counterweapon, the Browning M2, was a casualty of this same industrial abundance. It was not a specialized weapon. It was factory fresh, available in such overwhelming numbers that it was used casually, mounted on jeeps for convoy protection, utilized on half-tracks for infantry support, and given as standard heavy weaponry to Marine machine gun platoons. When American tanks arrived on Saipan, they were the latest variants of the Sherman, capable of shrugging off hits from the Japanese 37mm guns. The 37mm American anti-tank gun, designed in the 1930s, was already considered obsolete by the U.S. Army in Europe, where German armor was too thick. Yet, the Japanese 37mm Hago gun, the main armament, was still considered fully operational and effective by the Imperial Army. Colonel Goto and his men were going into the largest armored clash in the Pacific with a machine that, in American eyes, was already one generation past obsolete, and they were charging into a wall defended by the American equivalent of infantry support weapons. The inevitable collision would not just be a defeat, but a moment of brutal, material revelation that exposed the full magnitude of the deception they had been living under. The charge began at 0330 hours on June 17, 1944. 44 tanks, engines roaring, their tracks churning the coral dust, advanced against the perimeter held by the 2nd Marine Division. The Japanese tactics were bold and aggressive, a dense concentration of armor intended to punch through the American line before the support artillery and main tank reserves could react. Inside the Hago tanks, commanders stood in their cramped, solitary turrets, peering through vision slots, their faith in their armor absolute. They expected small arms fire to clatter harmlessly against the hull, perhaps forcing them to keep their hatches closed, but nothing more. What followed was a massacre that shattered not steel, but psychological reality. Marine machine gun crews, sighting their M2.50 caliber guns, opened fire. The heavy, steady thump-thump-thump of the M2 was immediately followed by the unique sound of the armor-piercing rounds hitting the 12mm Hago plates. Witnesses reported that the bullets didn't just penetrate, they went through the thin armor cleanly, creating entry holes and large, jagged exit wounds on the far side. One Marine gunner, positioned near the airfield, focused his tracers on a Hago's frontal plate. He later recounted seeing sparks flying inside the tank through the vision ports before the vehicle shuddered, slowed, and stopped, its diesel engine seized. The penetrating rounds had ripped through the engine compartment's thin decking. The psychological impact on the Japanese crews was immediate and devastating. Their tanks were not just being defeated, they were being unmade by a weapon they did not classify as a threat. The armored cocoon they had trusted suddenly became a steel coffin, its walls insufficient against the standard ammunition of their enemy. A single half-inch AP round that penetrated the armor became a lethal projectile, ricocheting, striking the rudimentary control levers, or hitting the cramped crew directly. The commander of one Hago was reportedly struck down in his turret by a .50 caliber round that entered the side armor and passed through him. He never knew what hit him. As the heavy machine guns halted the advance, the American M4 Shermans moved in, their 75mm guns reducing the remaining Japanese tanks to burning wreckage. The Japanese 37mm rounds bounced harmlessly off the Sherman's angled frontal armor, sometimes leaving small chips, but never penetrating. This was the irrefutable evidence. Not only were their light tanks vulnerable to infantry support weapons, but their main tank guns were entirely incapable of defeating the opponent's armor. It was an overwhelming, undeniable collision between the fantasy of station overcoming material reality, and the harsh, brutal fact of American industrial engineering. The Japanese counterattack, the largest armored effort they would ever mount in the Pacific, was over in less than 4 hours, leaving 31 destroyed tanks scattered across the beachhead. The psychological contract between the Japanese tanker and his machine was fundamentally broken. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The morning after the tank charge on June 17, 1944, Marines walked among the wreckage, and the truth of the Japanese armor doctrine was laid bare. Officers ordered their men to examine the destroyed Hagos closely. The clean, definitive holes punched through the 12mm armor were the physical evidence of the .50 caliber rounds. An American officer later summarized the revelation: "We found that the 50 caliber machine gun was just as good as a 37mm anti-tank gun against Japanese tanks." This simple, brutal fact instantly and forever changed the Marines' perception of Japanese armor. The fear factor, the psychological dread of facing enemy tanks, evaporated. Japanese armor was now downgraded from a critical threat requiring specialized assets to a mobile target susceptible to the heavy machine gun, a weapon abundant in every American unit. The psychological fallout among the surviving Japanese crews was profound. When Colonel Goto's surviving men were later captured or interrogated, intelligence officers noted a consistent pattern: a sense of betrayal and genuine shock. They had been told their tanks were adequate, they had witnessed firsthand that their equipment offered no protection against the standard heavy arms of the enemy. One captured tanker, a veteran of years of fighting in China, could not believe the truth. He told interrogators that the Americans must have developed some new secret weapon, some exotic ammunition disguised as a conventional machine gun round. His military mind could not accept the simple fact that the conventional American .50 caliber AP round possessed the energy and the material core to defeat his tank's armor. His training had taught him the impossibility of this outcome. The realization that their own leadership had sent them into battle with obsolete equipment, failing to grasp the material leap made by their enemy, was a devastating blow to the concept of imperial infallibility. This single, localized battle on the beaches of Saipan sent shockwaves through the entire Pacific theater. Intelligence reports confirming the effectiveness of the .50 caliber against the Hago and Chiha were disseminated rapidly. For the remainder of the war, Marines approached Japanese armor with supreme confidence, knowing they did not need to wait for a specialist bazooka team or a Sherman tank. Any infantry perimeter with a well-placed Browning M2 could now hold its own against a tank charge. The irony was complete: the same Japanese industrial constraint that had prioritized mobility and reliability over armor in the 1930s now led to the widespread adoption of a single, devastatingly effective counter-tactic in 1944. Japan's limited industrial capacity meant they could not build a replacement for the Hago in time, leaving their forces across the Pacific stuck with a tank that offered its crews no physical or psychological protection against the most common American weapon. The Hago became less a tank and more a self-propelled tomb, waiting for the inevitable, cleanly punched hole of a half-inch armor-piercing round. Even as the war raged in 1944, the Lockheed P-38 Lightning, despite its combat successes, remained plagued by its persistent hydraulic failure. This issue was fundamentally different from the Japanese armor problem. It was an internal, systemic crisis threatening to undermine the massive American investment in the aircraft. The hydraulic system, which controlled the landing gear, flaps, and supercharger intercoolers, was a network of high-pressure fluid lines operating at a nominal 1,500 psi. The failures, however, were notoriously intermittent, occurring perhaps once every 50 or 100 landings, often with fatal results. The problem was specifically the nose gear. It would either fail to extend fully and lock, or it would extend but collapse suddenly upon touchdown, creating a dangerous and embarrassing spectacle on runways across Europe and the Pacific. Lockheed's senior design engineers and maintenance chiefs were caught in a bureaucratic and technical nightmare. They performed continuous tests, dismantling entire hydraulic systems, replacing pumps, checking valves, and inspecting the main actuators. Their focus, rooted in traditional engineering diagnostics, was always on high-pressure failure. They assumed that if a component was going to leak, it would do so when stressed by the maximum operational pressure of 1,500 psi. The flaw was sought in cracked castings, porous seals, or fittings that stripped their threads under immense force. But under every high-pressure test, the system held flawlessly. The pressure gauge needles remained steady, and the system performed perfectly. The failure only occurred in the hands of the pilots, in the chaotic environment of landing approach, when the system pressure often dipped and fluctuated. The psychological reality for the pilots was one of profound mistrust in their machine. They loved the power, the twin engines, and the devastating nose-mounted firepower, but every single landing approach was a moment of sheer dread, a gamble that the nose gear would actually lock into place. This operational paralysis was unacceptable. By the end of 1943, the number of aircraft damaged or lost due to this persistent flaw was beginning to accumulate, leading to increasingly frustrated cables from operational commands in the field demanding a fix. The solution lay in recognizing that the failure was not a fracture under tension, but a weakness in the system's ability to maintain integrity under the seemingly benign conditions of low pressure. It required a fresh perspective, one unburdened by the assumptions of established hydraulic engineering. The task of finding the invisible leak eventually fell to the Stress Analysis Department, a section dedicated to the meticulous, often tedious, work of component testing. It was here that Elizabeth Betty Snyder was assigned a batch of seemingly routine proof tests on various P-38 hydraulic system components. Betty Snyder, a recent graduate from the University of California, Berkeley, was one of the many skilled women who had entered the field to support the massive wartime production effort. Her role was not to redesign the aircraft, but to verify that every small part met its stipulated material and pressure tolerance. The specific item she received was the hydraulic T-fitting, a small, seemingly insignificant junction point where the main fluid line branched toward the nose gear actuator. The fitting used a common connection technology of the time, a flared tube mated with a specialized copper sealing sleeve known as a ferrule. This ferrule was responsible for creating the high-pressure seal. According to the standing test protocols, Betty was required to perform a proof test up to 1,500 psi, the maximum operating pressure. She ran the test multiple times, subjecting the fitting to the required pressure, and each time, the system held pressure perfectly. The copper ferrule, under the immense pressure of the hydraulic fluid, was forced tightly against the tube in the fitting wall, creating a seal that was technically flawless. Had she simply signed off on the test sheet and moved on, the flaw would have remained buried. But Betty Snyder possessed the rigor of a true analyst. Instead of simply affirming the high-pressure tolerance, she decided to conduct a full-range analysis. She wanted to observe the component across the entire spectrum of its potential operational pressures, from zero up to the maximum. This methodology was not specifically required by the test sheet, but was driven by her scientific curiosity and training. She slowly began to release the pressure, monitoring the gauges and the exposed fitting with painstaking attention. This was the moment the years of assumption by senior engineers was about to be undone by focused, low-pressure observation. As the pressure in the system dropped slowly from 1,500 psi, past the 1,000 mark, and down toward the 500 psi range, Betty Snyder noticed a minute, almost invisible change. At the exact moment the pressure fell to a level common during a landing glide, between 400 and 600 psi, a tiny, almost imperceptible film of hydraulic fluid began to form around the brass nut connecting the ferrule fitting. This was the low-pressure weep. It was not a gushing leak, but a trickle, a bead of fluid that would momentarily appear before the pressure climbed again, or before the test was manually stopped. This discovery was revolutionary in its simplicity. It proved that the problem was not a failure of strength under high tension, but a failure of material resilience under low compression. The conventional copper ferrule was too soft, too malleable. While the high pressure of the fluid forced the copper to expand and create a tight seal, the moment the pressure dropped significantly, a common occurrence when the main pump cycled off during a landing approach, the copper component would relax or contract microscopically. This minuscule relaxation created a pathway for the hydraulic fluid to escape, allowing air to enter the line, or simply reducing the fluid volume enough to prevent the nose gear actuator from completing its stroke and locking securely. The intermittent nature of the failure in the field was now perfectly explained. If a pilot made a sharp turn or cycled the flaps, briefly raising the system pressure, the leak would seal itself. If the pilot made a smooth approach where the pressure naturally lagged, the weep would occur, leading to the catastrophic failure on the runway. Betty Snyder's observation, which contradicted decades of unstated engineering assumption, was the key. She hadn't found a fracture, she had found a behavioral flaw in the material itself under specific pressure dynamics. Her findings were quickly verified, leading to the immediate and urgent suspension of some production while the fix was engineered. The solution, thanks to Betty Snyder's definitive identification of the pressure dynamic, was straightforward but required a massive logistical effort. The material of the hydraulic ferrule had to be changed from soft, yielding copper to a harder, more resilient alloy. Lockheed engineers quickly settled on a specialized aluminum alloy, a material that possessed the necessary hardness to resist microscopic contraction when the system pressure dropped below the critical 500 psi threshold. This aluminum ferrule would maintain its seal across the full operating range of the hydraulic system, eliminating the low-pressure weep entirely. The cost of this discovery was not measured in dollars, but in the immediate operational disruption it caused. The fix was mandatory for every P-38 in existence, whether on the assembly line in Burbank, flying combat patrols over Rabaul, or stationed in depots in Britain. A total of over 5,000 P-38s that had already rolled off the production line required the replacement of this small, unassuming component. Urgent modification kits, containing the new aluminum ferrules and installation instructions, were rushed out to every field maintenance depot worldwide. Mechanics, working often under canvas in muddy, remote locations, had to meticulously cut into the hydraulic lines of every Lightning and replace the flawed copper part. The psychological contract between the pilot and the machine was finally restored. The nose gear failure rate, which had been a serious threat to the aircraft's operational readiness, plummeted to an acceptable minimum after the fleet-wide modification was completed in the latter half of 1944. This was the ultimate confirmation of Betty Snyder's contribution. She had not only solved a persistent technical mystery but had cleared the P-38 to become the tactical success it was designed to be, a long-range fighter and reconnaissance aircraft that required maximum pilot trust. The material change in a piece of metal less than an inch long had resolved a logistical crisis that had paralyzed thousands of aircraft and endangered the lives of every pilot who flew the twin-boom fighter. The irony of the P-38 hydraulic flaw is a textbook example of how critical technological victories are often achieved in obscurity. The aircraft's most famous achievements, like the long-range intercept of Admiral Isoroku Yamamoto in April 1943, were public, dramatic moments. Yet, the foundational fix that ensured the P-38 could operate reliably for the rest of the war came from the quiet, meticulous work of a young woman stress analyst in a stateside lab. Betty Snyder's name rarely appeared in the celebrated histories of Lockheed or the Army Air Forces. Her reward was not a medal or a promotion to a chief design post, but simply the successful completion of a difficult technical task. Her story is a reminder of the often unseen complexity of wartime logistics and engineering. The war demanded millions of components to work flawlessly, not just under ideal conditions, but across the full range of material and dynamic stress. The failure of the copper ferrule was a failure of assumption, the belief that the system would behave predictably outside of maximum stress parameters. Betty Snyder's rigor in testing beyond the required minimum demonstrated a professional integrity that saved the entire P-38 program from an internal, fatal flaw. The P-38 Lightning went on to fly until the end of the war, contributing massively to air superiority in both the European and Pacific theaters. It became a symbol of American air power and engineering ingenuity. But its reliability rested on the hard-won knowledge gained from that low-pressure weep. The legacy of Betty Snyder and her discovery is one of intellectual courage, the courage to question the established assumptions of senior engineers and the discipline to meticulously observe the most minute details. In the vast, roaring, high-stakes enterprise of the American war machine, the most critical truth was revealed not in a high-speed dive or a dogfight, but in the slow, painstaking drop of a pressure gauge on a workbench in California. The story of the P-38's hydraulic flaw is fundamentally a study in the irony of recognition. The men who flew the Lightning became legends. Richard Bong, Thomas Maguire, and other aces accumulated victories that filled newspaper headlines across the country, their fame built on the machine's speed and firepower. The men who designed the P-38, like Kelly Johnson, became engineering giants, their names synonymous with Lockheed's success. But the people who ensured the machine worked, the people who fixed the potentially fatal flaws, often remained anonymous. Betty Snyder was one of those essential, yet unsung, contributors. Her work was not glamorous, it was the quiet, methodical application of physics and observation that lacked the immediate, dramatic appeal of aerial combat. In the wartime narrative, which was heavily focused on the battlefield and the factory floor's sheer volume of output, the complex diagnostic work often went uncredited. The psychological reward for men like Kelly Johnson was seeing their vision soar. The psychological reward for Betty Snyder was the knowledge that her component testing protocols were sound, and that her observation of that minute low-pressure weep had resolved a systemic crisis. There was no victory parade for the aluminum ferrule. There was only the simple, profound fact that thousands of pilots were now landing safely because of her diligence. This reality, that a civilian, female stress analyst held the key to the operational success of a major combat aircraft, runs counter to the traditional memoir of the war, yet is absolutely central to the story of American technological triumph. The engineers who had initially missed the flaw were not incompetent, they were simply bound by the logical assumptions of their era, believing that the greatest stress point was the only point of failure. The 1,500 psi test figure had become a psychological barrier, preventing them from looking below that critical threshold. It took a new set of eyes, unburdened by past assumptions and focused entirely on the rigorous science of how the material behaved across the full range of stress, to find the answer. Betty Snyder's contribution underscores a principle often obscured by the roar of cannons. Modern warfare is won not just by brave soldiers, but by the relentless, anonymous pursuit of technical accuracy in the quiet laboratories of industry. Her subsequent career, continuing in engineering, was built on the foundation of this single, brilliant piece of wartime analysis that literally kept the Lightning in the air. The P-38 debacle highlights the colossal logistical demands of fighting a war on a global industrial scale. By the time Betty Snyder's discovery was verified and the solution implemented, the number of P-38s that required the new aluminum ferrule replacement was nearing 6,000 aircraft. This required not just the engineering of a new part, but the immediate cessation of production on the hydraulic sub-assembly, the creation of new tools and dies, and the establishment of a priority manufacturing line solely for this tiny, essential component. Then came the challenge of distribution. Modification kits, often termed mod kits, had to be compiled and shipped by air and sea to every Allied air base where the P-38 was operational. This meant delivering tens of thousands of these small parts, alongside detailed, precise instructions, to remote airfields in places like New Guinea, the Aleutians, and the Mediterranean. The logistical challenge was immense, a quiet war waged by cargo pilots, dockworkers, and maintenance chiefs against the clock. The entire war effort was a vast, moving machine where the failure of one small, inexpensive copper piece could paralyze a crucial asset, and the timely replacement of that piece by a 3-ounce part could restore critical operational capability. This was the antithesis of the Japanese approach, exemplified by the Hago tank. Japan was forced to conserve and accept obsolescence. The United States had the capacity to diagnose a problem, halt production, retool, manufacture a replacement, and distribute the fix globally, all within a matter of months. This ability to self-correct on a grand scale was arguably a greater weapon than any single gun or bomb. The story of the aluminum ferrule is not just about a technical fix, it is a profound demonstration of the logistical resilience and overwhelming industrial depth of the United States, an ability that the Axis powers simply could not match, and which ultimately determined the war's outcome. For the men flying the P-38, the hydraulic flaw was a profound breach of the psychological contract between the pilot and his machine. A fighter pilot's confidence is built on the absolute faith that his aircraft will perform as advertised under extreme duress. The P-38's persistent nose gear failure eroded this faith in a uniquely insidious way. It was not a failure of courage or skill, but a failure of the basic physics of the landing sequence, the moment the pilot required maximum mechanical reliability. Imagine the psychological reality of the final approach. The pilot is exhausted from a 6-hour combat mission, perhaps having survived a grueling dogfight. His speed is dropping, his altitude is critical, and the landing field is rapidly approaching. He throws the landing gear lever. He gets the main gear indication, green lights. But the nose gear indicator remains red. He pumps the emergency manual system, pushes the plane into a sharp maneuver to shock the gear loose, and still the nose gear remains elusive. This uncertainty, repeated across hundreds of pilots in multiple theaters, created a profound and debilitating stress. It was a crisis that added unnecessary, preventable risk to the most vulnerable phase of flight. The pilot had been promised a machine that was structurally sound. Betty Snyder's finding restored that promise. Once the aluminum ferrule modification was complete, the confidence returned. The green light for the nose wheel became a certainty, not a gamble. This restoration of confidence, though intangible, was essential to the P-38's combat effectiveness. A pilot who trusts his aircraft is a pilot who can focus entirely on the mission. The elimination of the nose gear anxiety freed the pilots to concentrate on the enemy and the rigors of long-range flight. The most significant function of the aluminum ferrule, therefore, was not mechanical, but psychological, stabilizing the faith of the airmen in the complex machine they relied upon for survival. The P-38 Flaw served as a stark, practical lesson for the entire field of American aerospace engineering, a lesson learned through the simple observation of a leak at low pressure. The principle that was relearned and then codified into new standards was this: maximum operational stress does not define all points of failure. Complex dynamic systems, especially those involving fluid power like hydraulics, must be tested across the entire operational envelope, from the point of highest static pressure down to the lowest active pressure point during the cycle. This shift in testing philosophy moved away from strictly proof testing a part's ultimate strength and moved toward analyzing its dynamic resilience and material behavior under cycling conditions. It reinforced the importance of stress analysis as a fully integrated, critical component of the design process, not merely a compliance check at the end. For hydraulic systems across all aircraft models and later, across other military equipment, the standard testing protocols were refined to include mandatory observation during pressure decay and minimum pressure simulation. The lesson was etched into the industry: if a problem is intermittent in the field, the cause is likely a dynamic anomaly, not a static fracture. The historical echo of this event is crucial. The Japanese tank designers, as discussed earlier, focused their specifications on resisting enemy fire from the front, neglecting the overall dynamic requirements of the battle space. Similarly, the Lockheed engineers focused on resisting 1,500 psi, neglecting the lower pressure reality of the landing sequence. In both cases, the failure resulted from a focus on an incomplete parameter set. The P-38 fix became a fundamental teaching moment: look beyond the obvious threat. Look at the full spectrum of the environment. The integrity of a fighting machine depends on the integrity of the knowledge that goes into every one of its smallest parts, a lesson delivered by a leak that could only be seen when the pressure was off. the story of Elizabeth Snyder and the P-38 hydraulic Flaw stands as a quiet but enduring testimony to the unsung heroes of the Second World War. The great battles were fought by men, but the technical war was fought by men and women across countless labs, workshops, and assembly lines, each tasked with ensuring that the tools of war were reliable and fit for purpose. Betty Snyder's observation, seemingly a footnote in the history of a renowned fighter, had direct, measurable, and life-saving consequences on the battlefield. Her legacy is that of the quintessential problem solver, a person who ignored assumption, applied pure scientific rigor, and delivered a solution that saved the aircraft program from within. The P-38 Lightning went on to fly successfully until VJ Day, its iconic silhouette defining the American air effort in the Pacific. Its reliability, once jeopardized by a piece of soft copper, was secured by a harder piece of aluminum, placed there because a young stress analyst chose to look a little closer, and a little longer, than anyone else. This quiet dignity of essential technical work, which ensures that the spectacular heroism of the pilots can take place safely, is the true heart of the war's industrial history. The Lightning's success ultimately rests not only on its speed or its guns, but on the meticulous honesty of a test bench in Burbank. Thank you for watching. For more tailored historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.